All right, welcome to GCP Online Meetup number 33. I'm Jonathan Cham, and I have a co-host today,
Stephanie Wong.
Yeah, thank you so much for joining. If you've been watching a lot of these, please subscribe to the channel. And we're just turning off our volumes right now, but we're super excited to have Prashant Dhingra here with us today. He's he's in our PSL organization. He's kind of the type of person that gets down in the weeds and just knows everything about kind of what customers are doing and all the details about getting just getting down and dirty. So Prashant, do you mind doing a quick introduction of yourself?
Thanks, Jonathan. Yes, my name is Prashant Dhingra. I work as a lead in machine learning team in Google. And today we will walk through a predictive maintenance demo and design. Thanks, Jonathan. Yes, my name is Prashant.
Oh, sorry about that. We had some audio issues for a second. Sorry about that. Yeah. So thank you for introducing yourself. And so I think for us, machine learning is obviously really important, and it's become kind of a staple here at Google when we talk to customers. And so I thought, hey, Prashant was kind of working on this really cool activity. Actually, Prashant, maybe you can tell us a little bit about how you got involved in this activity here with this oil rig.
Sure. So I've been working in machine learning since last 9 years. And there are a lot of scenarios which are very common across the industry. And in this era, when IoT is becoming popular and the cloud platform is powerful, there is a lot of value to do the predictive maintenance, because almost all manufacturing companies need this capability. By knowing when the machines are going to fail, they can improve the efficiency of operations and they can reduce the downtime. It is a common scenario which is required in all the industries. And then because sensor data is easily available, and with cloud we can easily ingest the sensor data, it is actually very easy to do machine learning on sensor data and predict when machines are going to fail.
Yeah, that's really interesting. I was actually talking to an airline customer, and they're also collecting a lot of sensor data from their airplanes and trying to do basically the same thing as what you're describing, is predictive analysis as to when they might do repairs or failures, and to prevent that. And that way they can keep their airplanes up as much as possible.
Yep, so was I with oil tanks as well, just trying to measure which ones were at warning level status so that their drivers didn't have to go and keep checking unnecessarily. So this is a use case that we commonly see in the industry nowadays.
Yeah. So Prashant, I heard that you play cricket and you're really good at cricket, but you also have a really awesome demo to show us. Isn't that right?
Yes, so we have a good demo. I used to play cricket, and nowadays, whenever I find a time, I try to play cricket. But today we'll walk through the demo, not a cricket.
I'd love to see a demo on your cricket skills, though.
Can we do machine learning on like a cricket related?
Actually, nowadays sports also use a lot of machine learning.
I'm sure.
To determine like what kind of a strategy the team should use, what kind of a approach a player should use. So machine learning is very popular in sports also.
Mm-hmm. Cool. Yeah, I'm excited to learn more about that. Maybe we'll do that as the next meetup.
Sure.
So yeah, let's see the demo. I think you're going to jump into the demo. You can share your screen.
Yes. So let's jump into the demo. Let me know when you can see my screen.
Yep. Let's see here. Yep, we can see your screen.
Okay. So this demo is about a oil company. That oil company has multiple oil rigs. Each oil rig has multiple machines. And the oil company wants to know when machines are going to fail, so that they can replace the machine or do the maintenance of the machine and improve the efficiency of the oil rig. So this demo is about an oil company. And first we will go through the demo, and then I will explain you the design, and I will explain you how the Google Cloud IoT platform and Google Cloud Machine Learning is used to build this solution. So here is a oil company, and on the map you can see they have 3 oil rigs. They all are in green stage. When I click on an oil rig, I can see that one machine is installed on this oil rig. If I click on a second oil rig, I can see 3 machines are installed here. I click on a third oil rig, there's one machine installed here. So it shows what is the status of a machine on this oil rig. If I click on a machine, I go inside a machine, and I can see the sensor data coming from the machine. This is a real-time sensor data coming from a machine installed on an oil rig. So there is a cable tension sensor, pressure sensor, temperature sensor, and viscosity sensors. By looking at it, operator know what is the health of the machine. And if I scroll down, we can also see the historical data for these machines. You can see the upper threshold and lower threshold. And you can see whether there is an anomaly or outlier in this data. And that also tells you whether the machine was behaving abnormally recently or in the past. So real-time data and historical data gives you a clear picture what is the health of the machine, whether machine is working or not. That gives a good insight to operator. At the same time, you also want to know what is going to happen in future. That's where the machine learning comes into the picture.
So this dashboard you're showing right now is just kind of the current state of the oil rig.
Yes.
Can you talk about, how the decision is made to, I guess you have to be a specialist in the oil rigs to know what you should be monitoring, right?
Yes. So I will quickly show you which sensors we used and how we shortlisted the feature. So by using these 4 sensor data, we built a DNN model, and then DNN model is predicting that this machine is going to last for another 40 weeks. And a company knows that it takes them almost a year to replace a machine. That's the reason it is in a warning stage. So now the oil company can plan for the maintenance or the replacement of this machine. Because we will not be here for 32 weeks in this demo. We are fast forwarding this demo, and within few minutes, you will see that this machine will die when it completes its life cycle. So there is a historical data, there is a real-time data, and there is a machine learning model. I will show you how we did the feature selection.
Can you quickly describe, you mentioned DNN, for those of, for our audience who isn't familiar with machine learning, I mean, that's the, just a neural network. Can you describe what DNN is at a high level?
DNN is a deep neural network. And in this model, we are using a DNN regressor model to find what is the remaining life of a machine. The advantage of using DNN is DNN can find complex relationship in data, which a traditional machine learning algorithm can't find. The second advantage of using DNN is that it can help you in determining which features are playing a role, which features have predictive power. So human insight always plays a role, but DNN can help you in finding more features which a human can't find. So those are the reason we use the DNN regressor model.
Thank you for that.
So here is a architecture. So you have seen the demo. The architecture behind the scene was the sensor data from the oil rig is coming. We use Cloud IoT core to ingest the data. Cloud PubSub is used for messaging. And then we have Cloud Data Flow to process the data. And BigQuery is used to store the data and build a big data solution. And we were using Google App Engine as a visualization engine. And this is a traditional IoT and big data solution. On top of that, we had added a machine learning model, the DNN regressor model, which Jonathan just talked about, that predicts what is the remaining life of a machine. So on the real-time data, we make that prediction and we feed it back into the BigQuery. And then we also continuously train on it. That makes it an intelligent predictive maintenance solution. Because not only you are seeing the health of the system, but you are also seeing what is the remaining life. Sometimes your prediction is right, sometimes your prediction is not right. So we continuously train a ML model, and over a period of time, the accuracy of the model improves.
So Prashant, we have a question, I guess a couple questions. How frequently do you collect the data?
So for depending upon the scenario, a team needs to make a call how frequently they need to train models. So real-time data is coming every few seconds. We are making prediction every few seconds. But we train on these kind of a scenario, we train once in a week. Okay. Because the sensor pattern doesn't change more often. Like in some business cases, it makes sense to train daily or even like a couple of times daily. But for a sensor data, once in a week is fine. So we train once in a week.
Mm-hmm. And so for those, for the audience who are familiar with the neural networks, how do you design the architecture in terms of layers and neurons, or is that more experimental?
It is a combination of both.
Mm-hmm.
We go through phases, like we first define a use case. After we define a use case, we define like what are our features or labels, and then we do the data exploration to see that those features has predictive power. And then we identify which kind of a model architecture we should build. So for example, if you are using a data where your model works on absolute values, so if your model is working on absolute value of temperature, you can use a standard DNN classifier or standard DNN regressor. But if your model doesn't work on absolute value of temperature, but it works on the spike in temperature, that means you need to use time series data, and then you need to use RNN or LSTM kind of a model. And the advantage in Google Cloud machine learning is it is built on TensorFlow. You learn TensorFlow once, and all these capabilities are built in. So you can build a DNN classifier, DNN regressor, or you can build a RNN or LSTM model very easily.
Great. And
how does it sort of handle kind of new data field inputs if you wanted to define a new data field from the sensors? Does it kind of adapt the model to new ingestion of data fields?
This is a very good question. So let me divide this into two pieces. First is the primary advantage of using machine learning solution is as data pattern changes, machine learning model adapts itself. So I'm not talking about adding new feature, but as your values of data changes. So for example, you had a machine that used to fail when certain temperature rise above certain threshold and few other parameters. Now you have a new version of a machine which is more robust. Machine learning model will automatically determine that this machine is more robust, its thresholds are different, its criteria for failing is different. So it will adapt to the different values of data. Now let's go back to the question which Stephanie asked, is if you add a new feature, how we will handle it. So generally when you add a new feature, you will add it into the model schema, and you will also add it into the model prediction. So there is a small change required here, and DNN is very helpful in this case also, because if you build a model using non-DNN method, let's say you build a model and you use random forest and then you use decision tree, and when you add new attributes, you will realize now your current algorithm doesn't work well on the new attribute. But DNN gives you this capability where you can add more attributes very easily. And not only you can add more attributes very easily, you can add different type of data sources. For example, DNN works well for not only for structured data, it works well for unstructured data like text and images. So DNN is much more powerful in handling multiple types of data. So when you need to add new type of signal, you will have to make a small change in the model features, but DNN makes the life easy because as you just need to define the new feature and whether it is a type continuous or it is type categorical, and then your model will adapt to it.
Okay. Yeah. Thank you.
Okay, so if there is no further question, we can quickly dive into the high-level design. If you want to build a predictive maintenance solution, what are the steps you should go through? So these are the high-level steps. You identify a use case. You capture thousands of good example and example of failure, and you create features and labels, and then train a model. You evaluate a model, and if the accuracy of the model is good, then you deploy the model and start making prediction, and it helps you in saving cost, improving efficiency, and reducing downtime. So this is an end-to-end steps you will use in a predictive maintenance solution. So let's deep dive onto these steps. If you want to build a predictive maintenance solution and you want to define a use case, these are the important things to capture. How will you use output of predictive maintenance? Will you just use it in a report? Will you use it to replace a machine? Will you use it to maintain a machine? Or will you just fire an alert so that somebody can look into it? So define in use case, how will you use the output of predictive maintenance solution? Then the most important thing is, what is the definition of breakdown? Because it can mean different things to different people. Breakdown might mean the machine has actually failed and now can't work. The breakdown might mean that machine is producing more heat or more noise, or breakdown might mean that machine is not fully operational, its efficiency is reduced. So what is the definition of breakdown for your use case? So define it. Then ensure that the signals you are capturing have patterns to show your breakdown, because the signal should correspond to your breakdown definition. Then determine how often you are collecting these signals, and then how much of normal and failure data you have. And if you have a good amount of normal and failure data, you are ready to go, and then you can proceed with building a predictive maintenance solution. If you have a very few example of failure, then there are techniques you can use to handle the class imbalance, and you can ensure that there are good proportion of normal and failure instances. So this will define your use case. Once you define your use case, just keep an eye on these three challenges: how you will collect data from equipment, how you will do feature creation, and then how you will build the model. When you use Google Cloud Platform, Google Cloud IoT Core and PubSub help you in collecting data. You can use BigQuery and Data Lab to prepare feature. We also have another tool called Data Prep that can also help you in transforming data. And then you can build a model using Cloud ML. Cloud ML is a managed service of TensorFlow, and it provides you DNN method, and it also allows you to build non-DNN machine learning model.
So Prashant, can you talk a little bit about the feature creation aspect? Because I think for collecting equipment, it kind of makes sense, but with feature creation and deep learning now, feature creation has kind of changed quite a bit. So how do customers use BigQuery and Data Lab for feature creation?
Sure. So in a traditional data warehousing, we use the term called data mart, where we had historical data, we create marts, and we store the values. Now, features, when we do the feature creation, that means we need to bring the data into a shape that a machine learning algorithm can consume. So for example, first you need to identify feature, and sometimes the raw feature works, and sometimes the raw feature doesn't work as it is, and you need to use craft new features. For example, so if you are collecting data from temperature and pressure, the temperature and pressure might signal that, okay, when machines are going to fail. Sometimes temperature and pressure raw data might not signal when machines are going to fail, but if you take their moving averages, or if you take like maximum amount of temperature that has been produced, or if you take the median of temperature, those might have a signal that this machine is degrading and it will fail over a period of time. So you need to determine what kind of a whether the raw feature has a predictive power, or you need to use mathematical function and craft new features, and then the new features might give you predictive power. Then the other dimension you need to look into is sometimes raw attributes alone doesn't have predictive power, but you build feature crosses. And feature crosses is a combination of two attributes together. So example is, if you have a mobile device and if you have a browser, and if you look patterns, you may not find pattern that there is a pattern in a mobile device usage or a browser usage, but you will realize that when some browser combination is used on a mobile device, there is a pattern. Similarly, the other example is, let's say you are trying to predict whether a yellow color car is a taxi or not. Now, if you combine the like location, New York car and a yellow color, you can predict that, okay, yes, it is a taxi. But if you do the same thing in a different city where the different color cars are used, you will not be able to predict if you are using the raw feature, but by using the feature crosses, you will be able to make prediction. So similarly, in predictive maintenance, using a feature cross of what make and model machine is, what kind of a configuration is used on that machine, or what kind of a load that is used on that machine, the feature cross of those things together can be a good feature. So these are the summary of techniques we use in feature creation, but feature creation takes like 70% of the time when we build a model. It is an important phase of machine learning model building.
Yeah, I hear from my customers that the the most, I guess, frustrating and cumbersome part is getting all that data and putting it, I guess they call it data wrangling, right?
Yes, so one needs to prepare the data, one needs to transform the data, and then one needs to identify the features, then one needs to identify feature crosses and the craft new features. That's where most of the work goes. And over a period of time, you will see that machine learning tool will become smarter and smarter. They will automate most of the things, but feature creation will remain there. So if you have a knowledge of, so many times we use statistics to determine what features are right. Sometimes we use domain knowledge, and many times we DNN also helps in determining what features have a predictive power. So most of the other pieces of model building will get automated, but feature creation is an area where a machine learning team needs to spend time on. Does it answer your question, Jonathan?
Yeah, no, that's great. Yeah, thanks for that. And I think, I mean, it's a little far-fetched, but even data flow could do some sort of, extract and transform and putting it into maybe features that you could use. So.
Yes, absolutely. And it's a very good point. In the architecture diagram I showed, we use data flow. Here I didn't mention the data flow. In general, what happens is we go through a data science phase in which we build a machine learning model, and in that phase we use data prep, data lab, and BigQuery to create a feature, and then when we operationalize it, we use it data flow to operationalize it so that the end-to-end things are automated. But many times during the data science phase also we end up using data flow. It is definitely used in the operationalization phase.
Great.
So when you're pushing data through data flow, and once the ETL is completed and you do have your feature list, is it getting pushed into Cloud ML, which also stores the data as well? Or is there another form of storage or database that will actually house the transformed data once it's ready?
Yes, so once we create a feature, we can store data into a Google Cloud Storage, or we can store data into BigQuery. And Cloud ML can get the data from storage or from BigQuery. It is easy to use it from storage. The advantage of using BigQuery is you have a one data store where you can do analytics as well as you can do machine learning. I always advise my customer that they should consider building a feature mart, which is similar to a data mart, because the features which we are creating are not only useful for a machine learning model, but a traditional BI team should also look into the transformed feature and should do analytics on them. So my suggestion to customer always is that use the transformed feature in a machine learning model, but also use it for analytics. And BigQuery is the best tool available in the market to do it, because you can do analytics in BigQuery and Cloud ML can directly consume the data from BigQuery.
Cool.
Okay, so we talked about a use case. We talked about like the 4 steps you need to go through, and then these are the 3 key challenges. So now, Jonathan, you earlier asked like how we determine what features to use. So in a predictive maintenance, if you take an example that if you want to know when this machine will die or when this machine will fail, our ultimate goal is we need to find features that have a predictive power or that shows the degrade. So examples are many times when machines get older, they produce more heat, noise, and vibration. Sometimes their speed get reduced, their efficiency get reduced, they start taking lesser load. So those are the features which has higher predictive power, and these are the first thing we should look for, that which features can show the degrade pattern. And once we know that, okay, which features show the degrade pattern, generally these are the data you are getting from sensors and you can use it for predictive maintenance. But also consider combining with other data as an individual feature or by doing a feature cross. So IoT data is coming to you every second. So this data should definitely will be used for predictive maintenance. But on top of that, consider using static data like make and model of a machine, because that might also play a role, that how what is the degrade path for that particular machine, what configuration is used to run that machine. And many times the machine manual and business rules has more details that can also be feed into the model. So there is a time series data, and then there is a static data. Then you should also consider using frequently updated data like usage history. For example, if there is a machine or an engine that has been used continuously 20 hours a day versus there is another engine which is used only 2 hours a day, it is likely that the engine that is used 20 hours a day probably is degrading faster. So this kind of frequently updated data you can feed into your model on a daily or weekly basis, that okay, this is the these many number of hours has been consumed on this particular engine, how much dwell time is there. On top of that, many times we put different types of load onto a machine or onto a equipment. For example, how many, if there is a vehicle, how many people use that vehicle? If there is a bus that is used by 100 people every day versus a bus that is used by 20 people every day, so probably the bus with 100 people load is degrading faster. Similarly, on a machine, if the load matters, then one can capture that load and get this frequently updated data and put into a machine learning model. Then there are occasionally updated data like maintenance history. If you have replaced the part, that might revive few things in a ML model, and machine might not degrade that faster. If a service is done, the machine might last longer. So these are the features to start with, but also consider using static data, frequently updated data, and occasionally updated data. I've just given a few examples here. Depending upon your domain, you probably can think of many more such examples, and then try to see which category they fit into and consider using that into a predictive maintenance solution.
That's great, Prashant. So just give you a time check. We have about 15 minutes left. We do have a question.
Okay.
The feature mart, sorry to step back, but the question was about the feature mart. And Pushkar says, are you saying to study the filters generated by the layers?
Okay, it's a very good question, and I also intend to write a detailed blog. Multiple customers have asked for it. So think of it, feature mart, as very similar to a data mart. The difference is, if you let me start with an example. If you are capturing heat and noise and vibration, and you are storing it in a data mart, that okay, how much values of these fields are, and you're storing it. And when you build a model, you realize that the feature cross of heat and noise together tells you when machines are going to fail. So suddenly a machine starts making more heat and more noise. So that is your transformed feature. So use your transformed feature and physically store into a mart. Example, BigQuery or any other data warehousing solution you use, and then do analytics on that. So feature mart is similar to a data mart. The difference is data marts were built for analytics for what happened in the past. You are building machine learning model, what is going to happen in the future, and you are transforming your data so that your algorithm can consume. So if you build a feature mart, and now your domain expert can see that how the heat and noise feature cross is changing over a period of time. So over a period of time, your business owner who earlier only knew about a standard data warehousing will become more knowledgeable about machine learning. They will know how features are playing a role. So let me know if it is not clear. So feature mart is similar to a data mart. In feature mart, you store the transformed feature which you feed into the first layer of machine learning model. I'm not saying that if you have 7 layers of machine learning model or like 3 layers of machine learning model, after every layer you store it. But the set of features you are passing it your model to train on, and the set of features you are passing your prediction API, those features you should store it into a feature mart.
Yeah, so I mean, my understanding of how they differ is obviously, a data mart kind of collects everything and it has a lot of information. Your feature mart is pretty much a subset of all of that with kind of transformations, and it's pretty much a database of features that you're going to feed into a machine learning model. So, I mean, would you consider it just basically a subset of a data mart?
Yes, absolutely. As you said, all the transformed feature you will store into a database, and what it enables you is Now you can do analysis on this feature mart and see what is the distribution of feature. It can help you in debugging when your model is not performing well, and it can make your business and domain user more knowledgeable about what is happening, how the predictions are made. So you can get insight from you. People ask that, okay, they want to get insight from the model, but they can get also a lot of insight from the transformed feature, which is a feature mart.
Great. Yep. Pushkar says thank you. So I think you answered his question.
Okay. So we already talked about this, that we should consider using raw attribute as a feature, but we should also consider crafting new features. So I just put a standard set of features here, but they're probably, depending upon your domain, you can think of other features like count, sum, minimum. For example, many times temperature value might be enough, but many times you may want to focus on minimum or maximum or average or median temperature. Many times you may want to focus on standard deviation, and many times you may want to focus on rolling average and tumbling average rather than focusing on the absolute values. So craft these features and see whether these gives you a better predictive power.
So it'd be like completing a calculation and then using that as a new feature.
Yes.
That's actually a tough problem though, right? I mean, how do you know when you need to, I don't know, take a feature, square it, or do a root of it, or multiply it by another feature? I mean, a lot of it is just kind of trial and error, right?
Yeah, a lot of it is trial and error, and many times there is a human insight. For example, if you work in a domain and you know that, okay, let's say there is a machine A and the value ranges from A to B, and for machine B, the value ranges from C to D, and sometimes they overlap, and you want to distinguish whether they are working or right or not. So like taking the averages or taking the moving averages of the values tells you whether machine is degrading or not.
So I guess this kind of ties back to the idea that this is sort of an iterative process, and it still really does need someone who understands sort of what they're looking for, or at least kind of understands the data that they're looking at and can figure out, okay, this kind of makes sense as a calculation to at least point us in the right direction for our model to run off of.
Yes, you're absolutely right. So human insight or domain expertise help. So if you have a domain expert, take their help to determine which kind of a computation you should do to get the right feature. Okay, so we talked about a use case, we talked about the feature creation and what kind of a transformation you can do it on a feature. And once you are ready with your feature, then you feed into a model, and DNN in a DNN model can find the complex relationship. So if you are doing a traditional machine learning, you probably need to do much more work in feature engineering. DNN makes it a little bit simpler. I'm not saying that you should not do feature engineering. You should still do feature engineering, but DNN helps in identifying features that which features have a predictive power. So for example, if you're not sure, you can put 50 different features and build a model and later see, okay, which 5 of them you should keep and remaining you should discard. So you build a model, you get a predicted value, and then regularly you see what is the difference between a predicted value and a actual value, and then basically keep refining the model. So this is a traditional cycle for building a model. Okay, so here is the example. Earlier I showed you oil rig example, and we talked about how you should select a feature. And this is a good diagram. So the data set we had for our demo, it has various sensors, 21 sensors. If you see the sensor 1, so I'm randomly picking 4 machines, red, blue, green, and yellow. You will see that the machines are starting here and machines die on these dates. So red machine died later, blue machine died earlier, and green before that, and yellow even before that. The sensor value 1 doesn't change when the machine was new and when the machine was old. So that tells me that this is not a feature that is showing the degrade. So probably it will not be useful in model. But if you look at sensor value 2, 3, and 4, you will see that as the machine is getting older and degrading, the values are rising. And you will see that in the first half, the values is rising slowly, but in the later half, the value is rising rapidly. And this makes them a good feature because, first of all, they show a degrade pattern. And it also tells me that if I build a model, my accuracy might not be good in the first half. So I might be predicting that the machine will last for 200 weeks and it actually lasts for 150 weeks. So my accuracy might be a little bit off. But as the machine get older, my accuracy will improve. And that is what we need, because when the machine get older and it is near failure, we want to predict it more accurately. So sensor 2, 3, and 4 makes them a good candidate. Similarly, sensor C, you will see that the value, sensor 7, the values are dropping as the machine is getting older. So data exploration phase and the domain expertise can help you in determining that these are the good features. And there were 21 sensors. There are more sensors also. You can see this pattern. When you do feature engineering, you may also want to remove features which are very, very highly correlated or a duplicate of each other. So when we build the today's model, the demo you have seen, this is built using these four features.
This sort of tells me that this isn't something, at least for ML, that you can wake up one day and say, hey, I want to do ML on my sensors, but this is something that you kind of over time have to look at historically at your data to at least jumpstart and help you identify features first before you can begin with building your model for ML use case.
Yes, absolutely. So data exploration phase is very important. And by going through it, you will know what is the shape of your data. Does it has predictive power or not?
Right.
Okay. One last thing to consider is when you define a use case, you also need to ensure that what are the matrices you are going to use, and then fine-tune your model to suit the metrics that are important for you. For example, in predictive maintenance, it's very common that there are 1% of failure or 0.5% of failure. And if you are choosing accuracy as a matrix, the model can predict everything as good and claim that 99.5% accuracy, but it is a bad model because it is not predicting failure, it is predicting everything as good. So accuracy is not a good measure in this case. So depending upon your goal, you may want to consider other matrices like TP rate, TN rate, FP rate, FN rate, or ROC curve. So TP rate will tell you percentage of correctly classified failure instances. So for example, if you are trying to predict aeroplane failure, this is the kind of matrices you want to go for, because you want to you want to pay attention to failure more. TN rate, percentage of correctly classified normal instances. If your cost of failure is low and cost of maintenance is high, for example, if I predict 10 machines will fail and only 7 fail, and we unnecessarily replace 3 machines, and that cost is very high, then you may want to pay attention to TN rate. Similarly, like FP rate and FN rate, depending upon your goal, whether your cost of maintenance is high or cost of failure is high, you should try to reduce FP rate and FN rate. The higher the TP, TN rate are and the lower the FP and FN rate are, the better it is. This is just a diagram that shows that if you have predicted that these machines will fail and these machines will not fail, so the yellow one will actually fail and the green that didn't fail, how to compute various matrices. Like there's a precision recall, TP rate, TN rate, and here are the formula to compute those. So you want to reduce the FP, false positive, if you have a high maintenance cost. And if you want to, if you have a high failure cost, you want to reduce the false negative. And you can compute precision and recall, or you can draw even a ROC curve. And here is a definition of precision and recall and when you should use it. Out of equipment classified will fail, what fraction were correct? If that is the question your business is asking, then you should pay attention to precision. Otherwise, you should pay attention to recall, which answers out of equipment class failed, what fraction the classifier actually pick it up. So consider using precision, recall, accuracy, TP rate, or TN rate, and see which one is more important for you. And FN score is another matrix, which is a harmonic mean of precision and recall.
So Prashant, James has a question on the chat about one of the benefits, obviously, of neural networks is you dump in a bunch of features and it will kind of uncover those features that are meaningful. Now, how do you actually figure out which of those features are meaningful? I mean, obviously with neural networks, you have weights, right? Higher the weights, the more impact it has on the output costs. But like from a practical standpoint, how do you do that?
Yeah, so there are a number of techniques you can use to determine which features are important. So there is a open source package available on web is called Lime. You can use to determine which features are playing more importance. You can, if you look into your model, many times by using the domain expertise, you can debug like which features are playing a role. I give you one simple example. Let's say I'm using 4 features in a model, and I do not know which one is more important and which one is less important. I can have a default values of these 4 features, and then let's say I make a dummy prediction call where I replace 3 with default value and 1 with the actual value. And earlier I was getting like 80% probability that a machine will fail, and now I am getting higher probability. Now I'm getting like 70% probability that machine will fail with only with 1 feature. That means that feature is contributing higher. And now I can, if I make 4 different calls, I will be able to debug for that particular instance. So not only at a model level, so for model level it is easy, but for that particular instance, which features is contributing, whether heat or noise is contributing more to the failure. Let me know if it was not clear. So if you have a n feature, for example, in this case 4, and you are getting certain prediction, you need to use some statistics to determine what should be the default values for those features. Then you make it 4 dummy prediction calls where you keep 1 actual values and 3 default values, 1 by 1 for all features, and see the difference. And then you can derive which features is signaling more about failure.
Yeah, I mean, ultimately it does boil down to the weights, right? In the
Yes.
neural network.
Yes, it boils down to the weights.
Right. Yeah. So Rama has a question too about normalizing the data. How are you doing that? I think there's probably some general best practices and techniques to normalizing data, but maybe you can comment on that.
Yes, there is a lot of domain expertise are required to normalize the data. There is no one single answer how you should normalize the data. But you want to ensure, like we use this example, that if you are doing house price prediction, and one of your feature is in the range of like 2,000 or 3,000 square feet, and another of your feature is number of bedroom, 2 bedroom and 3 bedroom, so you need to normalize it. So depending upon your domain and what kind of a features you are playing a role and what kind of a ranges those features has, you need to choose the right normalization mechanism.
Okay.
Okay, so we talked about, so this is a matrix for our model. I earlier mentioned it already that in the beginning, you will see that our error rate is high, but as the machine gets older, our error rate reduces. We also saw this pattern when we looked into the data exploration, that the degrade was less visible in the first half, and it became more and more visible and as the machine gets older. So using this, we were able to predict accurately when machine get older, but when the machine was new, the accuracy was lower. But for this scenario, this was a good outcome, because when the machine is new, it was enough for us to know that machine is not going to fail soon. How much remaining life is, even if there was a higher error, it was okay. But as machine become older, it tells us precisely when machine is going to fail. So this is RMSE is a important, is a common matrices we used when we find out the error rate in a regression model. So today we walked through this demo of oilrig. You saw the demo, you saw the architecture, and we went through the design. That you will define a use case, you will capture thousands of examples of failure in normal instances, and then you will train the model, and finally you will start making a prediction.
Yeah, that was really useful. I mean, I feel like with predictive maintenance, I mean, you can apply to anything, right? I mean, cars, automobiles, airplanes, trains, just
Cricket.
Yes, and actually it is predictive maintenance is easier because generally the sensors have a cleaner data. So whenever we apply machine learning where humans were involved, you will see there is a more discrepancy in the data because people act differently. But machine act in a conformed fashion, and you will see lesser data issue. There are lesser data compliance issue, and because the data is generally coming into a standard format and there are lesser data gaps, it is easy to build a predictive maintenance solution. And the value for the organization is very high because they can improve their efficiency.
We have a sort of a pretty technical question. It says, some of your data is similar to time series, vibration, rising temperatures, wondering if RNN would do justice to modeling.
Yeah, this is an excellent question. I will love to answer this. We actually build both model, RNN and the standard DNN regressor. So let me go back to this data again. When we build RNN or LSTM can remember the spike. And this can be very useful in making a prediction whether the machine is getting older and near the failure. What we noticed was the absolute values of temperature and pressure has a predictive power and not the spike. So we got the same accuracy in RNN and the same accuracy in standard DNN regressor. So that's the reason for this particular data, we decide to use DNN regressor because RNN is more costly to train and standard DNN regressor is less costly to train. But in predictive maintenance, wherever the spikes play a role, wherever you need to remember the previous values of data and that the sequence of data has a predictive power, you should use RNN or LSTM.
Okay. Yeah, and then I think we sort of covered this, but another question was, can you take a moment to elaborate on your choice of architecture for the model? So we talked about using a DNN regressor. Maybe Pushkar is asking more about specifics like neurons, number of neurons and layers. I'm guessing that you tried different ones and you came up with the one that performed the best.
Yes, so this example is a demo and it only uses 4 features.
Okay.
And that's the reason this is a very simple model. However, when we work with customers, we use multiple layers and it depends upon the number of features and the complexity in data. For example, with one customer, we had a 2-layer model. With another customer, we had a 4-layer model. But in this case, we just had 4 features, and it was a very simple model.
Got it. Okay, good for demos. All right. Well, we're running low on time. Well, we're pretty much out of time. I mean, Prashant, thank you so much for joining. Is there, any last words you want to tell our audience before we close out this meetup?
I think if audience is considering building a machine learning solution, predictive maintenance is one good solution to start with because it has a high value prop and it is easy to build.
Yeah, it seems like it's easy to justify, right? To invest in something like this, especially if it's going to help your automobiles or airplanes fly for longer and basically stay up running longer.
Yeah, it's kind of with this idea of like the 4th industrial revolution where, companies are starting to look at automating a lot of this stuff so that it can really help with time, labor, cost savings. So this is a really, I think, as you said, easy use case for you to get direct return on investment.
Yeah, good way to get promoted. I mean, if you can help save your company money, right?
Yes, and it is easy to deploy because you will see there are lesser privacy issue because wherever there is generally the sensor data, I'm not saying you should not consider the compliance issue, but generally sensor data has lesser compliance issue than other types of data.
Yeah, yeah, probably less than personal data, of course.
Yes, and if you're talking sensor data on a machine, so if an enterprise owns the machine, they probably will have lesser risk in just using that data and hiring a company to build a model, because it's only about machine heat and temperature.
Right.
Oh, that's great. Yeah, we're getting a lot of thank yous for the good presentation, Prashant. If you like this video, please subscribe and click the thumbs up. We're happy to hear from you if you want to hear about different topics, or if you actually want to present yourself. We're super excited to have you actually present, especially if you're a customer of GCP or you're a user of GCP and you have something really cool that you want to show. We're all ears. So thank you.
Thank you, everyone.
Yep. Bye.
Thanks a lot. Bye.